Welcome back to another exciting episode of Dave Does Math from Home. This is part 2 of our video on section 4.3. We're talking about derivative tests. Instead of jumping right into another example where we can use the first derivative test, I want to talk about second derivatives for a while, because the other test we're going to use is called the second derivative test, and it's probably not going to make a ton of sense unless we talk about what second derivatives mean and how graphically second derivatives can be interpreted. And then once we have that established, then we can talk about what the second derivative test is checking for, and then we'll be able to use both tests on a given example so that you can see how they compare and what they both look like. So second derivatives in second derivatives in Newton's notation, you'd say f double prime of x or y double prime. In Leibniz's notation, you'd say d squared y dx squared. This means the second derivative of y with respect to x twice. The squared on the bottom is because when we start doing derivatives on multivariable functions in Calc 3, we'll have things like z as a function of both x and y. And so you'll be able to take derivatives with respect to x or with respect to y or both. And you indicate what the derivative is with respect to with this thing on the bottom. So for now, we're only doing derivatives of y with respect to x because we're still in single variable calculus. But the reason that we're squaring this dx on the bottom is because it's with respect to x twice. So this is what second derivatives look like. But we need to talk about what they mean. A second derivative measures something about a function that is called concavity. Concavity is about how the function curves. So if we have a function that's going from here to here, there's three ways we can get from here to here. The most obvious way we can get from there to there is a straight line. Straight lines have no concavity. They're straight. They don't curve at all. So all three of these from here to here graphs are going to be increasing. So all three of these have positive first derivatives because the function is increasing. It's going up. So we're just going to look at how it can get up. If it goes in a straight line, it has no concavity. This is neutral. This is 0. If it goes below where the straight line would be, this is called concave up. And this means that the second derivative is positive. So this means that the second derivative is 0. Straight lines have concavity 0, or have second derivative equals 0, so no concavity. If it goes below the straight line, so it curves upward, that is concave up, and that means the second derivative is positive. If it goes above where the straight line would be, this is concave down, and this means that the second derivative is negative. So it's all about how they curve. If you connect 2 points on your graph with a straight line and look at whether your graph is above or below the straight line, you should get a sense of whether or not this thing is concave. Which is, hopefully this connects to your sort of, if you have any, your previous ideas of what the word concave means. I was first exposed to this word concave or concavity in respect to lenses or shapes. This is a concave lens, because if you connect 2 points in it, the line might be outside of it. This is convex, because if you connect 2 points, the line is always inside the shape. So this idea of concavity is about, if you connect 2 points inside the shape with a straight line, does that line ever exit the shape? When we're dealing with functions, we don't have like enclosed shapes. We just have squiggles and lines. But we can still talk about, if you connect 2 points on this squiggle with a straight line, is the straight line above or below your squiggle? And that's the idea of concavity. So if we look at a standard issue cubic, this is probably something like y equals x cubed minus 4x or something. This point right here, which should be at the origin if I was drawing more carefully, this point right here is called the inflection point. Because this is where the concavity changes from concave down. Everywhere to the left of this point, if you pick 2 points on this graph and connect them with a line, the line is always going to be below. So everything to the left of this point is concave down. Everything to the right of this point is concave up. If you pick any 2 points to the right of the inflection point and connect them with a straight line, the straight line is above the graph. So everything to the left is concave down, everything to the right is concave up. That's why this is the inflection point. So here we have f double prime of x is less than 0. The second derivative is negative back here. Here, the second derivative is positive. And at this point right here, which again should be 0, the second derivative is 0. And we can test this. Y prime is 3x squared minus 4. Y double prime is 6x, which checks out. If you plug negative numbers in, you'll get a negative concavity. If you plug positive numbers in, you get positive concavity. And if you plug in 0, you'll get a concavity of 0, or a second derivative of 0, which means you have the inflection point. This is concavity. This is what inflection and second derivatives mean. So now we need to talk about how we're going to use this information. And hopefully this graph, hopefully I haven't drawn too many little dotted lines on this. We can still use this graph to see what's going on. If you have a critical point here on a section of graph that is always concave down means it's kind of got this frowny face to it. So if you have a critical point in there, that critical point must be a maximum. If you have a critical point in this section of graph that is concave up means that it's sort of a smiley face. If you have a critical point in there, that means it's a minimum. Which is, if you think about this strictly in terms of the signs of things, it seems a little bit backwards. That when you do a second derivative test, a negative result means that you have a maximum, and a positive result means that you have a minimum. It seems a little twisted, but if you think about, when I was taking calculus, I would get this confused all the time. I would do second derivative tests, and I'd be like, oh, it's a positive number. Positive numbers are bigger than negative numbers. I must have a maximum. I lost so many unnecessary points on tests because of this. So I would encourage you to think about these in terms of shapes. If you have a negative second derivative, don't think about maximums and minimums. Think about the shape. Negative second derivative means concave down. It means you're doing a frowny face. The dot on the frowny face means that you have a maximum. If you're doing the second derivative test and you get a positive number here, positive numbers means that you're concave up, means you're doing a smiley face, means your critical point is a minimum. That's the second derivative test in theory. Let's see what it looks like in practice. Okay, here I have for us a function. I want to know where this function has local maximums and where this function has local minimums. First, I need critical points, so I'm going to take a derivative and set it equal to 0. This will give me negative x cubed after the coefficient and the power cancel. This will give me 6x squared and minus 8x. This is my first derivative. I'm setting this to 0. I'm going to factor out a negative x, which leaves me with x squared minus 6x plus 8. And that should factor into x minus 2 and x minus 4. So my critical points are x equals 2 and 4. And don't forget about this guy. This is a mistake I commonly see students make. When they factor out an x from all of this, they sort of forget that that x contributes critical points. This does contribute a critical point. If x is 0, because of this piece, the whole thing is 0. So we can factor it out, but don't forget about it. It's still important. If you factor out a coefficient, no one cares about that. Coefficients are extremely ignorable. They don't give you critical points. But if you're factoring out x's, those do give you critical points. So these are my 3 critical points. And to figure out which one is a maximum or a minimum, I need to find a second derivative, if we're going to use the second derivative test, and then plug these values into that second derivative. So I'll start with the second derivative. I need to use the original first derivative, not a simplified or modified version of it. The original second derivative should be negative 3x squared plus 12x minus 8. This is y double prime. So I need to plug some numbers in. Say f double prime. I'm going to switch from y's to f's so that I can plug numbers in. F double prime of 0 is negative 8. And here's the good news. Like the first derivative test, I don't actually care what the number is specifically. All I care about is whether it's negative or positive. So it's not important that it's negative 8. It's just important that it's negative. Negative means that this is concave down, which looks like this. So this must be a maximum. Let's do f double prime of 2. When I plug in 2, I'll get negative 12 plus 24 is positive 12 minus 8 is 4. So this is concave up, which looks like a smiley face, which means I have a local minimum. And And when I plug in 4, f double prime of 4, I will get 16, negative 48 plus 48 is 0, minus 8, and back to negative 8. So this is once again concave down. Looks like a frowny face. This is my other maximum. So without getting into any real details of this graph, it looks like I have a maximum at 0, a minimum at 2, a maximum at 0, and then it probably does this. Does that match what we think should be happening? Yeah. I have a 4th degree polynomial. I'm sort of expecting 3 wiggles, 3 humps. So I got my 3 humps, and the end behavior should be hammer time. It's going down on the left and the right. So yeah, this information matches what I'm expecting to see out of this polynomial. I should plug these 3 numbers into the original function to find the y values of these local max and mins, but this video is about to cut itself short, so I'm gonna beat it to that. We're gonna do a part 3 where we'll look at a function and find maximums and minimums using both the first derivative test and the second derivative test at the same time, so we can see how those compare. So stay tuned for that.